on Riemannian symmetric space. With blessings of all my teachers, I would like to begin the talk. Okay, so last lecture actually we have seen that this group sp2nc sp2nc is non-compact, pseudo-algebraic, and closed under conjugate transpose. Okay, so today we will see that sp2nc is connected. Okay, for that recall. So let A belongs to MNH. Okay. A and let A, B, A prime and B prime, this belongs to Cn. These are n dimension belongs to Cn, and let A of A plus JB, this is equal to say U plus JB. U B belongs to Cn. Okay. And we have seen that this will imply that ZA AB is equal to UB. And this Z is the embedding from MNH to this M to MC. Okay, so we have seen this in previous lectures, so let me show you that. Here actually, U of Z plus ZW is equal to U plus JB. This implies if and only ZU of ZW is equal to UB. So we have seen that, and I am using that. Okay, so similarly, let A plus JB prime is equal to U prime plus JB prime. This implies ZA of A prime B prime equal to U prime B prime. Okay. Now I want to calculate this A of A plus JB and A of A prime plus JB prime. Inner product in Hn. This is the Hn in the n-dimensional quaternionic vector space, and that is really what U plus JB. This is U prime plus JB prime in Hn, and this is really something like U plus JB bar. This is the quaternionic conjugate plus U prime plus JB prime. So U bar plus JB bar dot U prime plus JB prime. Okay, so what is JB bar? So B is a okay. So let B is equal to say B1, B2, Bn. Okay, so JB is equal to JB1, JB2, and JBn. Okay, so now if you take bar, this will be like this, So this is we know that this PQ bar is equal to Q bar P bar. I am using that. So V1 bar J bar, V2 bar J bar, and Vn bar J bar. Okay, so and J bar is equal to minus J, so I will get minus of V1 bar J and minus of V2 bar J dot 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 minus of, so let us write it clearly a little bit. So this will be minus of V1 bar J, because J bar is equal to minus J, minus of V2 bar J minus of Vn bar j. Okay, so I have also told you that okay, if A is a complex matrix, some complex matrix M cross N, not necessarily square matrix, then Aj is equal to J A bar. Okay, so this is A bar J is equal to J. So we will use that thing. If you use that thing, because V1, V2, Vn are complex, so we will get that JB bar is equal to, so JB bar is equal to, so minus of JV1, JV2 and JVn. Okay. So this is the minus of J. So JB bar is equal to minus of JB. You remember this part? We will use this thing. Okay, so this is the thing. So you get what? So this is U bar. So U bar minus of JB dot U bar plus JB prime. Okay. So U bar dot U prime plus U bar dot JB minus JB dot U prime minus JB dot JB prime. Okay, so this is U bar dot U prime, and this U
It should
bar.
be U bar dot J V prime, right?
Yes, yes, yes. Thanks. So U bar. So U bar dot JB prime, same thing as this is U bar J dot B prime. I write that. So U bar J dot B prime minus JB dot U prime minus, similarly this is this will be JBJ dot B prime. Okay. JB. Okay, so my same argument U bar dot JB prime is something like that. So I should have written in the, okay, so let us see. So let us write this one more time. So U bar dot U prime plus U bar J dot B prime plus this is minus JB dot U prime minus JBJ dot B prime. I told you that this is the A, if A belongs to, okay, A is a bad notation. T belongs to some M cross NC, Tj is equal to Zt bar. Okay, so I will use this thing now. U bar dot U prime. So U bar J is equal to JU U prime minus JV dot U prime, and this will be minus of JV bar dot B prime. So U bar U dot U prime plus JU dot B prime minus JV dot U prime, and minus J square is equal to plus 1 B bar dot B prime. So you write that U bar dot U prime plus B bar dot B prime plus J into U dot B prime minus B dot U prime. And so look at this first thing carefully. This thing. So this thing is the inner product of UV and U prime V prime on Cn. Second thing is the sympletic part. U WV U prime V prime. This is the sympletic form defining sp2nc. Okay, W is the sympletic form corresponds to sp2nc. To sp2nc. Okay. So now you use that thing. UB is equal to what? ZA of AB. So I write that ZA of AB, ZA of A prime B prime plus J of, okay, so let us write J into W ZA AB ZA A prime B prime. Okay. So this is much I am getting. So let us write that in a phase line. So what I am getting, A plus JB into A plus JB prime, A prime J prime B prime, inner part in HN. So this I am getting ZA AB ZA A prime B prime in CN, okay, plus let us write this it as Z W ZA AB ZA A prime B prime. So this is called star. We call this is star. So from above we have the following observation. From star we have the following observation. Actually, suppose some matrix A preserves the inner product on HN. Okay? That means A belongs to SPN. If A belongs to SPN, A preserves the inner product on HN. Then that will, this implies that ZA will preserve inner product on CN, and ZA also preserves the symplectic form. Okay, so that means A belongs to SPN if and only if ZA belongs to U2N, and this is and this ZA belongs to SP2NC. So actually here actually I have, this is not CN, this is C2N. Number. This is C2N, not UN. So the observation, so A belongs to SPN if and only if ZA belongs to what? U2N intersection SP2NC. Okay, I call this 1. Okay. So from this thing, from 1 it is immediate. So that okay, so from 1 it is clear that Z of SPN is contained inside subset of U2N intersection SP2NC. Okay, so I call this as 2. Now I want to show the converse. Okay, so from 1 it is clear that Z of SPN is contained inside U2N intersection SP2NC. Now I want to show the converse. So just wait, I will drink words. Okay, so for the converse, let T belongs to what U to N intersection SP to NC. Okay, so as T belongs to U to N, so that means T star is equal to identity. T star T is identity, that is same thing as T star is equal to identity. Now if I will take bar in both sides, so I will get T bar T transpose is equal to identity. Okay. Now since T belongs to SP to NC, this will imply that T transpose JT is equal to J by definition. So I will multiply T bar both sides. T bar T transpose JT and T bar Z. So but T bar T transpose is identity, so I will use that. So I will get JT is equal to T bar J. So T is actually a complex matrix, but JT is equal to T bar J. That will imply that this T is equal to ZA for some A belongs to MNH. Okay. So this is the criterion for Z of MNH. That it will be T belongs to Z of MNH if and only ZT is equal to T bar Z. So now as this T, okay, as this ZA is equal to T belongs to U2N intersection SP2NC. This is by hypothesis because I have taken the T from U2N intersection SP2NC. That implies by that observation 1, this A belongs to SPN. Okay, so here actually this A belongs to SPN if and only ZA belongs to U2N intersection SP2NC. So by 1 in this case. Okay, so if A belongs to SPN, this implies T is equal to ZA. This belongs to Z of SPN. Okay. Now I have started an element from U to N intersection to SP to NC. And I am getting that it is Z SPN. That implies that U to N intersection SP to NC. This is subset of Z of SPN. So, and we have also proved the converse side 2, and I call this is 3. So from 2 and 3 we get Z of SPN is equal to U to N intersection SP2NC. So this is the required result. So hence we proved. Hence we have solved the following proposition. This is SPN SP2NC intersection U2N is equal to SPN. Now SPN is connected, so we have proved this thing. So this is connected. Now SP2NC is really pseudo-algebraic and closed under conjugate transpose. So this implies, so thus SP2NC is really connected by polar decomposition. And pi1 of SP2NC is really I1 of SP. Now this is the thing actually. Okay, another thing. So determinant, I have. I told you that if something preserves a bilinear form, non-linear bilinear form, and that automorphism group is, if you take determinant of that automorphism group, it will map to 1 minus 1 is continuous. And since SP2 and C is connected, we get determinant of whole SP2 and C is 1. So by restricting this condition that determinant is equal to 1, we will not get any other group. Okay, so this is the thing. So now another, let us say, fact. So let B be a finite dimensional vector space over field K, where K is equal to either R or C. K is equal to R or C. Equipped with a non-degenerate bilinear form B. Non-degenerate skew symmetric bilinear form B. Then dimension of B is even. So how to show that? This is very easier thing. So what I'm saying that if on a finite dimensional vector space over a field K, where K is all the R or C, we have a non-degenerate skew symmetric bilinear form, then dimension of B is even. So proof is very simple. Say we fix a ordered basis S. Okay, so with respect to S, let P be the corresponding matrix. Be the matrix associated to B. Since B is non-degenerate and the skew symmetric, non-degenerate and skew symmetric, I will get that P transpose P is so P transpose is equal to minus P, and P is invertible, and determinant of P is not 0. So this P is invertible. Now since P transpose is equal to minus P, I can take determinant in both sides. Determinant of P transpose equal to determinant of minus P. So determinant of P transpose is determinant of P, and determinant of minus P is equal to minus 1 to the power dimension of V into determinant of P, but determinant of P is non-zero, so I can cancel out both sides. So that means minus 1 to the power dimension of B is equal to 1, so dimension of B is equal to 0. Okay. So to possess a non-degenerate symmetric bilinear form, the vector space has to be even dimension. So theorem. So let B be an B be a 2n dimensional vector space over field K, where K is equal to R or C, equipped with a non-degenerate Q symmetric bilinear form B on it, then there exists an ordered basis S is equal to V1, V2, Vn, W1, W2, Wn, so that B of Bi Vj is equal to B of Wi Wj is equal to 0 or 1 less Ij less than equal to n, and B of Vi Wj is equal to delta I. Okay, so okay, proof let us just look at the statement that if B is a two-dimensional vector space or field K equipped with a non-regressive symmetric bilinear form B on it, then there exists an ordered basis S is equal to V1, V2, Vn, W1, W2, Wn, so that B of Bi Bj is equal to B of Wi Wj is equal to 0, B of Vi Wj is equal to delta I. Okay. So proof C Huffman-Kunje. This is done in Huffman-Kunje. So remark this. First remark this basis S in the previous theorem is called symplectic basis. Okay, so second term, there exists precisely one non-degenerate skew symmetric bilinear form on an even dimensional vector space over field K. Okay, and here K is either R or C up to equivalence. So this is the same thing. The third thing is let S be as in the previous theorem. Then ought S B is SP to NK. Okay, and the associated matrix and the matrix associated to B with respect to S is minus J. So this is the similar remark as to that of bilinear form, symmetric bilinear form, and actually we have actually exhausted most example of classical Lie group except one group actually except one group. So now we will move towards the calculating this fundamental group of this so-called symplectic group. Okay, so let us okay. So the thing is if you look, what are the examples we have covered? We have, it falls into two categories. There are compact groups and non-compact groups. In the compact group, we have this covered SON, ON, SUN, UN, and SPN. In the non-compact category, you have this GLNR, GL plus NR, SLNR, OPQ, SOPQ, SO0PQ, SP2NR, GLNC, SLNC, UPQ, Q, SUP, Q, SP2NC, GLNH, SLNH, and SP2P, Q. Okay, so and these groups ON, GLNR, which are written in the color blue color, ON, GLNR, OPQ, SOP, Q, these are not connected. Okay, and you know that fundamental group, for definition of fundamental group involves path connected spaces and connected spaces. For that reason, actually, we will only calculate the fundamental group for connected non-compact groups, connected groups, sorry. Both compact and non-compact group. Now, so another thing you just understand that. So, so, so let G be a non-compact group, okay. Non-compact connected group. Okay, so we have seen that pi naught of pi 1 of G is equal to pi 1 of G intersection UN. Okay, so and we have explicitly calculated what is G intersection UN, and G intersection UN is really this is something, this is given in terms of Cartesian product of some compact connected groups. Okay, for instance, for SU P comma Q intersection QP plus Q, this is, we have given this SUP plus SUQ and cross circle something. So G intersection UN is really uh, given in terms of Cartesian product of this compact group. For that reason, if we can calculate the fundamental group of these compact groups, then we are done. Okay, so we have to do that. So let us do that. Okay, so we will first start from SON. So first proposition. Okay, let A belongs to SO3. So then uh, there exists an uh, there exists V belongs to S2, so that S2 means unit sphere, so that AB is equal to V. Okay, proof suffices to show that A has eigenvalue 1. So this is because if you get the non-zero vector AB is equal to B, then you can scale it where B not equal to 0 belongs to R3, and you can scale it to get an vector in S2, unit vector. So suffices to show that A has eigenvalue 1. Now observe that A has a characteristic polynomial of odd degree, and you know that odd degree polynomial has uh, a real root. So since characteristic polynomial of A has an odd degree, therefore thus A has a real eigenvalue lambda is equal to lambda c. Okay. Now since A belongs to SO3, this mod of lambda is equal to 1. So this will, and lambda is real. So this will be lambda is equal to 1 or minus 1. So if lambda is equal to 1, so we are done because we wanted to prove that 1 is an eigenvalue of A. If lambda is equal to -1, then we have two cases. We have other two cases. So other two eigenvalues are real. Okay, two are complex. First, let us see. Or other two eigenvalues are because the thing is, if one eigenvalue is complex, then you know that eigenvalues occurs in complex conjugate. So it will force that two eigenvalue has to be complex. So there are these are the two cases. Other two eigenvalues are complex, or other two eigenvalues are real. In this case, if other two eigenvalues are complex, then you will have e to the power I theta and e to the power minus theta are other roots. And if you look at the determinant of this matrix A, and in this case -1 e to the power I theta into the power minus I theta, the determinant of A will be -1, and this case is not possible. So this case is not possible. So if other two eigenvalues are real, so we have also here are two cases that everything is -1. So this is -1 or at least 1. Okay. So everything is -1, and since if everything is -1, then determinant will be -1, and this is also not possible. So not possible. So last case will be there. So A will have an eigenvalue 1. So this is clear. So Riju, is it clear? Riju?
Yes, Muna.
So let us give some discussion. Let theta belongs to minus pi to pi. So I really think this r theta is equal to the cos theta and sin theta, minus sin theta and cos theta. So what is this? This is geometrically. So geometrically, this is a rotation of plane R2 by an angle theta. Okay, so this is SO2 is equal to r theta, so that theta belongs to minus pi to pi. Usually people write 0 to 2 pi, but I am taking minus pi to pi, but because I have a reason for that. So SO2 matrices are nothing but the set of all rotations of the plane R2. Okay, so first thing is use r pi is equal to r of minus pi. Okay, so second thing is r theta as an eigenvalue e to the power I theta and e to the power minus I theta. It's clear. Third thing is if theta belongs to 0 to pi, then it will have a unique representation. Okay. For instance, r pi has two representations, r pi and r minus pi, but theta strictly in between, minus pi to pi, open interval minus pi to pi. So it will have a uniqueness. So if theta belongs to minus pi to pi and r theta is equal to r theta prime or some theta belongs to, here I am taking close minus pi, theta prime belongs to pi, then this implies theta is equal to theta prime. Okay, this is clear. So okay, so let 0 not equal to b belongs to r3. and theta belongs to say minus pi to pi. So pay some attention here. Let r b comma theta be the linear operator which fixes the vector v fixes v and rotates the plane perpendicular to v, that is v part, by an angle theta. So let r b theta be the linear operator which fixes v and rotates the plane perpendicular to v, that is v part, by an angle theta. So this is a linear operator. And another thing is here actually v is an arbitrary vector on R3. So the thing is we are taking theta positive and negative. So while rotating, we have to assign a direction where actually in that direction theta will be positive, and in the opposite direction theta is negative. If you are in a plane, then you can simply say that this is if you rotate clockwise, then theta is positive. If you rotate anti-clockwise, then theta is negative. But here actually there is a there is some difficulty. So to show that that, let us draw this thing. How do you do that? So first you suppose, so this is my plane and this is my vector b. Okay. So what you and this plane is my v path. Okay. So you can this v path will rotate in this direction, or you may rotate in this direction. So you have to assign a direction where it is positive. So what you do, what one does is just to take this plane v, vector v, and this is plane my v path. Okay. In place of this vector v, you just imagine a screw. Okay. Screw with the head of that screw is that vector, arrow of the vector. You just in place of this head, you just imagine that that is the arrow of that vector p. Okay. Now, okay, you rotate that. You assign a direction. Suppose in this direction, you rotate the screw in this direction, and if the screw comes out of the plane, then that you will assign that is positive direction of rotation. And if screw goes inside the plane, then you assign that direction is the uh, direction of rotation is negative. So what I'm okay. So what I'm saying that, see, the thing is you have to assign a direction of rotation which is positive. For that, in place of B, you fix a screw and rotate that rotate in a direction. If in that direction the screw comes out of the plane, then that direction is positive. If the screw goes into the plane, that direction is negative. So let me write that. So okay, sorry. Screw comes out of the plane. Direction of theta is positive.
This is called right hand thumb up.
Yeah. Yeah, people use this right hand coordinate system and left hand coordinate system, but I get confused with this thing. So always I from the school days actually I confused with framings, left hand, right hand, all those things. So for that reason actually I do it like this.
Okay, that's better.
The right hand thing you mean? Okay, so that I just Yes. So sorry if I am doing very trivial things. Okay. So
Yes, this is also good. No? So,
yeah. So okay. So this is the thing, and it is so observe that r b theta belongs to SO3 because in a suitable orthonormal basis, this r p theta has matrix representation is equal to, this is will like this 1 0 0 r theta. So for that reason, this is belongs to SO3. Now there are some repetitions are there. So for instance, observe first thing is observe r of b theta is equal to r of alpha b theta, where alpha belongs to alpha is a positive number. Alpha positive number. Then if some operator fixes b, then it will fixes alpha b, and okay, so b power p is equal to alpha b power. For that reason, our b comma theta is equal to. Now second thing is r of b theta is equal to r of b minus theta, minus b minus theta. Okay. Second thing, you can check that in your free time, because I told you that how to assign a direction of theta. So and here actual theta belongs to minus pi to pi, and v belongs to r3. So there are some of our repetitions. So to avoid that, to avoid repetition, we take v belongs to s2 and theta belongs to minus pi to pi. So theta belongs to 0 to pi, because this rb theta, because of this condition rb theta is equal to r of minus b minus theta. Okay, so okay, so let us write a phase space then. Okay, let S be the collection. Okay, R b theta, where b belongs to S2, then norm of b is 1, and theta belongs to 0 to pi. Okay, so first thing is your R b0 is equal to R b prime 0. There are certain repetitions. This is R b0 and R b prime 0 is equal to identity. Okay. Second thing is what? Okay, so R b pi. This is same thing as R of minus b minus pi by that 2, and this same thing as r of minus b minus pi plus 2 pi rotation, and this same thing as r minus b pi. So r of b pi is equal to r of minus b pi. Okay, so first thing I am getting rb comma 0 is equal to rb prime comma 0 is the identity, and rb comma pi is equal to r of minus b pi. There are certain repetitions, and whatever elements left, there is only one representation. So let me write that. Third, so let v belongs to s2 and theta belongs to say 0 to pi. Okay, then if then t is equal to rv comma theta has only one representation. Okay, precisely what does it mean? Precisely, if rv theta is equal to rv prime theta prime, or some p prime belongs to s2 and theta prime belongs to 0 to pi, This implies V is equal to V prime and theta is equal to theta prime. Okay, so observe that here I am taking V belongs to S2, it is the same thing, but I am taking a rotation in between 0 to pi, strictly in between 0 to pi, then that will have only one dependent. This is precisely means that. So I will leave this thing and I will just uh, give an hint, okay, because this is easier to do. So a hint that, so this T has eigenvalue since theta is between 0 to pi, strictly in between 0 to, T has an eigenvalue 1 e to the power I theta and e to the power minus I theta. Now if you take this n1t, this is so that tw w, so that tw is equal to w, then this uh, dimension of n1t is equal to 1. This is clear because t has eigenvalue 1, and then you really, so now if rb theta is equal to rb prime theta prime, then t will then this is my t. So this, if we call that operator t, this will both fix v and v prime, and v and v prime belongs to n1 tree. But you have taken that v and v prime belongs to S2. Therefore, one is either v will be v prime or v will be minus v prime, and you have given some restriction on theta, and using that you are to prove that this rb comma theta has a unique representation. I have told you all the arguments, just you need to write that. Okay, so this is the thing. Okay, so now okay, we have to little bit discuss about little bit about algebraic topology. So you know this RP3. Okay, so this discussion ends here. So RP3, I take this a four-dimensional ball of radius r in R4. Okay, so I take that a four-dimensional sphere. Sorry, not ball. Sorry, this is sphere. Sphere of radius r in R4, and this is really homomorphic to S3. SR, and this is homomorphic to S3 in R4, and you just identify the antipodal points. Then you get RP3. This is the standard representation. You just identify this antipodal point. So RP3 is equal to, so this is RP3. This is equal to S0R. This identifies Z into minus Z. Okay. This is the cosine topology. Usually people take up radius 1, but I am taking radius of R. So now you can also do that same thing. You just take at the upper hemisphere, okay, and you identify antipodal points of the equator. So this will be like this. So this will be upper hemisphere. Hemisphere. So cosine Z to minus Z, and Z belongs to where? The equator. You just identify the, and in this case, okay, this E stands for equator. E stands for equator. And in this case, equator is homomorphic to S2, lower dimensional speed. So this is my description of RP3. Now you just flatten that upper hemisphere to a ball. Okay, so that you will get this thing. This, so you will get another thing of another representation of RP. You just flatten that upper part to a ball, only excluding the means equator. So this will be some B3 R closed ball of radius R Okay, and you have to identify that antipodal points of boundary. I really don't. So this is thing, and so you this is really like this. Okay, so you have to really identify the antipodal points of. So this will be B3R by del B. Okay, so identify Z2 minus Z, and Z belongs to a del B3R bar. Okay. So this is my final. We will use this thing. So RP3. So what I am getting this RP3 is equal to, this is 3-dimensional ball of radius R, and I am identifying the antipodal points of the boundary sphere, and so Z belongs to del P3. This description we will use for RP3. Now listen to, okay, so now pay some attention here. I define a map, define F from this P3, sorry, pi B3 ball of radius pi to SO3 by f of x is equal to identity if x is equal to 0, or you define this R of x by norm x. Okay. So you take this thing, you take this ball of radius pi, okay, closed ball, and suppose this is my point x, you join that point and you will get some direction that is x by norm x, and that f of x is the operator that will fix this vector x by norm x, and it will rotate the plane perpendicular to x by norm x by angle norm x. Okay. Now norm x is in between 0 to pi because of because we are taking x from B3 closed pi. Okay. Okay. Now suppose you take this r v theta and you perturb this v little bit, v prime, and theta little bit theta prime. So if you perturb v little bit v prime, theta little bit theta prime, then you expect that this change is really this perturbation depends continuously on v and theta. Okay, so I am not going to prove that. Just you use your imagination a little bit. So that means, so clearly f is a continuous function. Okay. So f is a continuous function. Claim f is onto. So to show that, let A belong to SO3. So by one of our previous proposition, there exists B belongs to S2, so that AB is equal to B. So let W is equal to B for. Now if I restrict A to W, check that A restriction to W belongs to SOW, and since and okay, and what is dimension of W? And this dimension of, and since dimension of W is equal to what, 2, so A rotates W by an angle theta. This implies and theta is equal to minus pi to pi. Okay. So yes, sir.
What is SOW?
SOW is equal to V per. This is the plane perpendicular to the vector B.
That is a special orthogonal group on the vector space W of dimension 2.
Okay.
Is this Jayant? May I know who was asking?
I'm Sanjay.
Oh, Sanjay da, Pushti da. Okay. So arrow dash W and W by an angle theta belongs to minus pi to pi. So this implies so A is equal to RB theta. So theta belongs to minus pi to pi. Now, if necessary, changing B to minus P, we assume that theta belongs to 0 to pi. Okay, that means this implies F is onto. Okay, because if okay, so one step little bit okay. Theta belongs to 0 to pi, so okay, let x is equal to say what theta b, then check fx is equal to what fx is equal to your a. Okay, fx is equal to what? This is r of x by norm x into x. This is equal to your a. Okay, I am getting confused. This is b. Okay, rb theta. This is going to be. Okay, so you have to probably argue if x is equal to 0, then if theta is equal to 0, uh,
That is identity.
identity. So you have to argue. So okay. So this is fx is equal to a. So then thus f is on 2. Okay. So now let z belongs to, so f is continuous and on 2. Okay. So let z belongs to del p3 closure of pi. So what is f of z? F of z is equal to r z by norm z and the norm z. This is norm z is equal to pi. So this is r of z by pi into pi. So since f of minus z is equal to r of minus z by norm z and minus, so r of minus z by pi is equal to pi. Now I have since r of v pi is equal to r of minus p pi, so this implies f of z is equal to f of minus z for z belongs to this boundary of this the ball pi. So this means, and what is rp3? Rp3 is equal to you are really taking this ball of radius pi in r3 and you are identifying antipodal point of the boundary. So for that reason, that f will induce a continuous, and since f is on 2, this map is on 2 map f tilde from rp3 to what? rp3 to so3. So here actually I am using this rp3 is equal to b3 closure pi z identified with minus z, z belongs to del b. Tapendu, is it clear? Tapendu or Tapendu is not there? Pritam?
Clear.
Okay, so if we will induce a continuous optimizer from this thing. So now if actually we have seen that, yeah, you look at this property 3. Okay, you have seen that if theta belongs to 0 to pi, okay, so this thing is RV theta has a unique representation. Means if you take this RP3 is what? This you take this ball and you identify that boundary sphere in antipodal points, and if you take some point inside, then because of that unique RV theta has unique only one representation, this map will be 1 1. So this map will be 1 1. So using property 3 of RV theta, you see that f tilde is 1 1. Tilde from RP3 to SO3 is 1 1. God. Okay, so we get f tilde is a continuous 1 1 and 1 2 map. Now as RP3 is host of, now RP3 is compact and SO3 is host of, this f tilde is a homeomorphism. So that means RP3 is homeomorphic to SO3. So that means pi 1 of RP3 is equal to pi 1 of SO3. And you know that pi 1 of RPN is equal to Z, where n is equal to 1, and Z2, where n greater than or equal to 2. So this implies pi 1 of SO3 is equal to Z2. So this actually I got this pi 1 of SO3 is equal to Z2. So now we want to define actually you can get this uh, you can conclude that pi 1 of SO3 from other ways also, but that will use some Lie theory, like, so if you know a little bit Lie theory, SU2 plus minus identity if you take, and this will be homeomorphic to SO3, and there are some abstract theorems that will tell you that pi 1 of SO3 is plus minus identity, and that is actually Z2, but we are not, since we do not know those theories, so we should not really I am not going into this. Okay, so pi 1 of SO3 is equal to Z2. So now there is some, we want to discuss something called higher homotopy group. So we will borrow some results from algebraic topology time to time. So you let X be a path connected topological space. Okay. So how do you construct this fundamental group? So you let us say P1, you take all the paths, all the loops from 0 1 to X. Okay. Now let B belongs to x be fixed. So let x be path connected topological space, and you fix a base point b belongs to x. You take all the paths from gamma 0 1 to x, so that this is continuous, and gamma 0 is equal to gamma 1 is equal to b. Okay, so on this set P1 you define an equivalence relation. Okay, so we define some homotopic equivalence relation on P1, and you balance relation on P1 and we get pi 1x. We get the fundamental group. Okay, so since gamma is a map from 0 1 to s, and this gamma 0 is equal to gamma 1 is equal to b, then you can really say that P1 is nothing but gamma is a map from s1 to x. You can think gamma is a continuous map from s1 to x, and gamma 1 is equal to b. And basically you are really uh, defining this homotopic equivalence relation on this set P1, where gamma is a s1 to x. Okay, now so since this is the thing, now you want to define the higher homotopic group. So analogously you take this gamma from Sn to x, where this is a continuous. Okay, so and you take this gamma of u1 is equal to b. Un is this vector 1 0 0 0 0. Okay, so on Pn we define an equivalence relation and associate a group INX to the to INX to it. Okay, so and this INX is called nth homotopic group. And here in this case, this is really n greater than equal to 1. Group for n equal to 1. And since x, I have assumed that this is the path connected space. So this implies this pi nx is okay, since so I will take 5 to 10 minutes more because I have to we will finish something, right? Since this x is path connected, this pi nx will be independent of the base point P. Base point P. Okay, so there is a thing, and there is a notion of pi 0x. So this is pi nx for n greater than or equal to 1. So this pi 0x and pi 0x really okay, here actually x is any topological space, so let not necessarily path connected. Topological space and not necessarily path connected. Necessarily. Path connected. And what is pi naught x? This is the set of all path components of x. So pi naught x is really x cosine space of you. This is a cosine space of x where y is related to g if and only if y and z belongs to the same path component. So now another thing, but we are interested. So let x is equal to g. Okay. Let G be the Lie group. Okay. And in this setup we will, so let G be a Lie group and let G naught be a connected be the connected component of identity in G. Identity in G. So that means so it is known that we can so check that G naught is a closed normal subgroup of G. This is a very easier exercise. In fact, it is true in the category of topological group. Closeness, for closeness, you need this G is a Lie group. So then check that G naught is a closed normal subgroup of G. Then what will be pi 0 G? Pi 0 G by definition set of all path components of the thing of G. The pi naught of G is equal to G mod G naught. So in this setup, and G mod G naught is since G mod G naught is a group. So in this set, this will imply that pi naught G in this setup is a group. Okay, so this is all about.
It is discrete group.
It is a discrete group. That is also important. Pi naught is a discrete group. This is it. Thanks. So we have in this setup G is a Lie group, and we have defined higher homotopy groups. And I want to really quote some result from algebraic topology. I also do not know the proof also. So let G be a Lie group and H be a closed subgroup of G. Okay. So then we have the following math. Then we have the following math. So you first start from H, and there is an inclusion map I, G, and P is equal to G by H. Okay. In such a situation, so using algebraic topology, using the topology, one can get a long exact sequence, and I will sequence as follows. Okay, so how to get that long sequence? So you start from the nth homotopy group, say, and there will be something from left. I am not writing this. You will understand what will be in the left. So you will start from pi nh. Okay, then you will be pi n g, then pi n g by h. Okay, it's the nth level, and this will be induced by this map I. So this is I star n. Let us say this will be p star n. Okay, and then you will go to the n minus level, and for that there will be some boundary map delta. So this will be pi n minus 1 h. So I n minus 1 star, and I am going to the n minus 1 level. I1 minus j and p n minus 1 star I n minus 1 g by h. Okay, so now again there will be some boundary map delta, and this will be something I n minus 2h an icon. Okay, so this is a very useful tool in fact, and you will, it is a very powerful thing. So you can calculate fundamental groups of various topological spaces using this thing. So pi n minus 2 g by s, and there will be something from right. And this in star, pn star, all are group homomorphism. These are really group homomorphism for n greater than or equal to 1. For n. Okay. So this is the tool we will use that. So okay, so now still we are in the same setup. So let in this setup let G be a Lie group and H be a closed subgroup of G. So let us start the thing chain from the pi 2. Okay, what we will get? So I will get this pi 2 of H. This will be pi 2 of G, a pi 2 of G by S. Okay. And there will be some boundary map delta. That will be pi 1 of H, and this will be pi 1 of G and pi 1 of G by H. Okay, so this will be pi naught of H. So that is not required pi naught of H, but it is true that it will go to pi naught of H also. So suppose pi 2 of G by H is equal to 0, this is equal to 0, and pi 1 of G by H is 0. So let pi 2 of G by H is equal to 0 is equal to pi 1 of G by H. So this implies then the sequence we get the so the long result sequence will be then the exact sequence will be this 0, this is pi 1 H and pi 1 of G and 0, and this will be some map I1 star I have called, but this is not. So this is a group. So this means I1 star is a group isomorphism because left hand side are 0 and this 0, and this is the exact sequence. So this implies I1H is isomorphic to I1G. So let us write that proposition. Okay, so thus we have put the following proposition. So let us see proposition. So let G be a Lie group and H be a closed subgroup of G, so that I2 G by H is equal to 0 is equal to I1 of G by H. Then okay, so then I1G is equal to I1 of H. So we have proved this thing. So and actually today I don't have much time. So tomorrow we will see application of this theorem, and we will finish the calculation of fundamental group. And tomorrow we'll move
Mona,
to yes sir.
pi 1G is equal to or isomorphic? Okay, it comes from the inclusion. Okay.
Yes sir. Actually I am writing equal to, I should write isomorphic, but that is equal to. Okay, is there any question? Pratham, will I start? Will I stop sharing?